Everyone, in this lecture I'm going to explain you the pulse code modulation. So pulse code modulation systems are not completely digital systems, as amplitude, width or positions of the pulses transmitted may vary continuously with baseband signals. Variation. So I assume that you might know it, but if you are not aware of it, then I will explain PAM also. So as we know, PAM is the simplest of pulse modulation system. So what are PAM signals? The PAM signals are basically, we use PAM signal. PAM signals are first quantized and then coded. Coded mostly in binary method, which basically converts them to pulse code modulation system, which is PCM system. So if we have to explain the principle of your pulse code modulation, then suppose we have this systems like this. Let me take it in the form of more, it will be better in the form of, so we have this, let's say we have, so if I have to draw it, so let's say I have these levels 1, 2, 3, they are equally spaced. My drawing might not be right. 4, so it might be 7 volts, then 6 volts, 5 volts, 4 volts, 3 volts, 2 volts and 0 volts. And we have a pulse amplitude modulated signal like this. Sorry, I didn't mention here. might be like that. And then you might have amplitude levels like this. Okay, so you can see that let us assume that this PAM signal, the PAM signal amplitude lies between minus 0.5 volts to 7.5 volt. Okay, and let's say we divide it into quantization level of it into quantization level quantization levels 8. Pulse between minus 0.5 to 0.5 volts are considered as 0 volt. Between 0.5 volts to 1.5 volt as 1 volt, and so on. Okay, and while we are doing it, we have assumed that as per probability theory that the pulse having exact values as 0.5, 1.5, etc., the pulses as will never occur. Thus any pulse can be approximated to one of the values of quantization levels, 0 volt, 1 volt, etc. Okay, now if you see at the pulses in the diagram, and we see that the pulses A and B, C, let's say this is close to if I just improve it more, let's say it's close to 3.7. This hole is 3.7 volts. This one is close to 1.2 or maybe 1.1 something, and the last one is close to, let's say, 5.6 volts. Okay, now so basically what we will do is that we will approximate them, and we will consider according to the range we defined here and the pulses range we are doing here. We will make it equals to 4 volts, we will consider it equals to 1 volts, and we will make it equals to 6 volts. So what we are doing is basically we are introducing a quantization error. So these then are known as quantized pulses. So they are not anymore the actual pulses or actual PAM signals, they are quantized pulses. So these quantized pulses are then encoding, and the most popular code which we used is, everyone knows, is binary coding. Okay, now if you aware of that, the binary coding of numbers, so let's say my quantization levels are defined here, level, and binary code is given here. Then we have level 0, 1. So we will basically have, let me try if I can write quantization 0, 1, 2, 3, 4, 5, 6, 7, and corresponding to that I assume that all of you know 0, 0, 0, 0, 1, 0, 1, 0, 1 0 1 1 1 double 0 1 0 1 1 1 0 and triple 1. Okay, these are the codes. So these encoding values are combination of binary bits, or can say of 0 and 1, and basically we transmit them. Okay, so basically what we are doing is that we are in digital systems. We are basically working on transmitting 1 and 0, which means presence of signal, presence or absence of signal. Okay, so the presence of the signal is denoted by 1 and absence of the signal is denoted by 0. Okay, so now if I have to show it in the form of waveform, let's say I am transmitting a 100. Okay, so 100 is, and then we are transmitting, let's say, 3 signals A, B and C, and their values are correspondingly 1 0 0 0 0 0 0 1 and C is 1 1 0. So we are transmitting these 3 signals, and when we are transmitting the signals, or can say pulses, that there is a time slot allocated to each bit. So each bit is getting a specific time slot to be transmitted, and a portion of which is a guard time. Guard time means that there should not be an overlapping between the 2 signals. Okay, so basically if, let's say, I'm sending A or something first, so if I have to explain it in the form of the plot, so we will have, it brought me here, so it will be something like this. Then let's say my amplitude is A here. Okay, so it's 1, then we have a 0, which is, and then we have another 0. So why I put the information in that way is that we will start from here. Let me draw the remaining ones. So it's 0, then I'm writing it here, and I'm writing another one here. In a similar way, if I have to write 1, then let's say 0 here, and 1 will be here, so it was 0. Then the third one is 1, then 1, and let's say 0 is here. So if I have to plot their waveforms, okay, so it's basically your, this is your A, this is your B, and this is your C. Okay, but what we are doing is that C will have, let's say, this, then A will have this, and then there's a gap between these two, and they are of equal width, remember that please. Okay, so how you define it is that let's say this all is your, this much will be your word time slot, means the total time slot for A. Okay, then you will have, this is your bit time slot, this, and then there will be something here. So this is your bit time slot. Okay, and if I have to be more precise, then this basically time is your bit guard time, so that the bits don't overlap with each other. In a similar way, if you see, let's say, sorry, I didn't put it wrongly a bit. So let's say it's somewhere here, and the next bit starts from here. So this is your word guard time. So when we transmit any information in digital system, we make sure that there is a guard time between the two bits, and there is a guard time between two pulses also. Like A, B, and C are three different pulses, so there should be a guard time between them also. Okay. Now, the major advantage of PCM system is that the information does not lie in any property of the pulse. The information